Yeah. I think he's recording all of them, just so you know.
I think
Yeah.
everybody's
It's
ready
like,
for Struvite.
yeah, I think everybody's ready. My presentation's tomorrow at 3:00, and there's not gonna be anybody here.
Well, I got
I'm
it
like,
there by then.
well, that's what I was gonna say. So I live in Jersey, right? I live an hour south, and I was like, if I wasn't presenting at 3:00, I'd be leaving probably at that time just to avoid traffic.
We probably have to, because we're already past start time. We're already past start time. Oh, yeah.
Yeah, and I'll try to, because I have the signs for 5 minutes, 2 minutes, and time's up. I'll give you a couple extra minutes.
I'm gonna try to be pretty quick. Mine's a high overview to get to apps cool chemistry stuff. So.
Yeah, that's good. Where'd Bill go?
Okay, on this I just hit the space bar and it'll drop us right through.
I think so. And then there is a pointer, I thought. Oh, it's right there. Got the pointer.
Blind people in the crowd.
Okay, everybody, we're gonna get going. Okay, next up is Jamie Belden. His bio is not in our pamphlet, but luckily we have something for it. Jamie Belden is in his 6th year of his 2nd stint as operations supervisor for the City of Wichita's Sewage Treatment Division, where he manages the operations of the city's 4 water reclamation facilities, biosolids land application program, and assists with project management and pretreatment functions. Previously, he has held positions as a pretreatment specialist and operations supervisor for the City of Wichita, environmental health and safety manager for CNH America, and public works superintendent for the City of Rose Hill, Kansas. Please welcome Jamie Belden.
All right. Well, thanks everybody. It's a pleasure to be here. It's a little bit out of my norm being outside of Kansas and being in New Jersey, but and if you look at the title of this presentation, it's a little bit different than what you have in your brochure. And the reason for that is this actually started out with us looking at a struvite removal program. Okay, we looked at how can we minimize struvite through the use of ferric chloride in our system. And when we did that, it grew into a much larger project. We started to see benefits much further beyond where we're at. And I won't go too deep into that because I don't want to take my co-presenter Af's thunder on that. Okay, so just to give you an overview of the City of Wichita Sewage Treatment Division. Currently, we operate 4 wastewater treatment plants, and we have our Grove Street pump station. The Grove Street pump station is just a really large pump station that takes the flow down to our main plant, which is our Lower Arkansas Water Quality Reclamation Facility, or Plant 2. And that's actually the original plant that the City of Wichita built in 1932. We also operate the Lower Arkansas Water Quality Reclamation Facility, or Plant 2, Cowskin Creek Water Quality Reclamation Facility, Plant 3, 4 Mile Creek Water Quality Reclamation Facility, Plant 4, and then we have a scalping facility out by our airport, which is our Mid-Continent Water Quality Reclamation Facility, and which is Plant 5, and that's currently mothballed, and that's a whole nother presentation in itself. So I wanted to give you an overview of our collection system and our different plants. If you look at all this green area up here, that is the collection system that comes down to our sewage treatment plant number 2, or the lower arc facility that we'll be focusing on today. The reason I wanted to show you the other facilities is this area up here is our Cowskin Creek Water Quality Reclamation Facility. It just got solids dewatering at it. Prior to that, we would haul liquid solids, dump it in a manhole in the north part of our collection system. It would flow all the way down to plant 2 to be processed. Out here is our 4 Mile Creek Water Quality Reclamation Facility, and right now we're in the process of finishing up an upgrade to that facility that will include solids handling. It will include recuperative thickening, but we haven't got all that installed yet. So currently we are hauling the solids, or liquids, sludge to our collection system, which is coming to plant 2. In all of our collection system, and this becomes important, because Wichita is so flat, we have a lot of miles of collection system, and they're very flat, and all those solids going into the collection system also produce a lot of odors for us that we have to deal with. Okay, so an overview of the Plant 2 facility. It's a designed 54 million gallon a day flow. We have an average of about 30 million gallons a day. We don't expect it to build out because we're going to more satellite facilities that we can manage a little bit more effectively. Our max flow is 62 million gallons a day, and we are a trickling filter plant with extended aeration. Right now, we're only doing nitrification. We aren't doing any biological nutrient removal. And we have a mix of primary solids and activated sludge, about a 50-50 mix that goes to our DAF for thickening. We start out about 1.5 to 2%, thicken to about 6%. Then it goes into our 4 anaerobic digesters. And then it goes across our belt filter presses. And much of the equipment we still have in place, much of the equipment that we're utilizing is original from the 1950s and 60s upgrades. To give you a biosolids overview of what we have at our facility, we're the main treatment, collection, and distribution system for all of our solids. So we have cities of all around the area that either truck cake to us, or they discharge their liquid solids into our collection system, and it comes down to be processed at plant number 2. We do about 35,000 wet tons per year, which equates to about 5,500 dry tons per year. And we haul about, in 2017, it was one of our heavier years, but we brought 1,067 end dumps to our farm fields for land application. And we have about 30 to 32 tons per truck, at about $520 a ton for our hauling costs. So that's about $176,000 a year. We're pretty fortunate because being in a rural area like that, we very rarely haul our sludge more than probably 10 to 20 miles to be land applied. But one thing that's unique about us is we don't charge our farmers anything for it. They have never gone to that, and since the inception of the program. So we actually haul it, we spread it, and we disc it in all for the farmers at no charge. We are relooking at that because it is a large burden on us. Okay, so obviously Struvite has been an issue in a lot of plants, and Struvite has become a much larger issue for us, especially as our infrastructure ends up aging. We've got some old belt filter presses. We have those nylon coated rollers that the Struvite gets on, and there's really no way to get it off of them besides replacing the rollers. So it's extremely labor intensive for our guys to clean those. Our equipment, we've started to see the life cycle of all our parts decrease dramatically, and obviously it decreases the drainage through your belt filter press as you're building up the Struvite through. And here's just some pictures of some different Struvite deposits on our different rollers, on our presses, and some of our pipe work. So we were looking at options to remove Struvite within our facility. And one of the options that we had looked at was using ferric chloride to feed into the system. And we saw some pretty good results, but when we did the trial, the company we did the trial with, they provided the chemical, the feed equipment, static mixers, and a reaction vessel, which was nothing more than pretty much an air compressor tank that we modified and put some baffles in, and some technical assistance. And we showed a big improvement in our Struvite by binding up the phosphorus, but we also saw a lot of improvements in dewatering as well. So I titled this "How Struvite Saved the Day" because in the middle of all of this, we started having failures, mass failures of our belt filter presses. We started having frames breaking down where we were having to weld frames. We started having all these other issues. But we were performing the trial on just one press at that point in time. And with the decrease in Struvite and the ease of cleaning we were seeing, we expected to see that. One thing we did not expect to see is the significant increase in our cake dryness that was going across the belt filter presses, and we were able to almost double our throughput per press. So we expected to see a few percent solids increase. We expected to see a little bit of throughput, but we were able to almost arm out. So due to the necessity for the throughput on the presses, we expanded this to all 4 of our presses immediately because we had to keep sludge going through. We had no other way to dispose of it. And our average gallons per minute across the presses went from 75 to about 140 gallons per minute with only a 30% polymer increase. And right now, we are actually using a manic polymer versus an emulsion, so we're also in the process of doing a trial to see a difference between that. And our cake solids went from about 18, and 18 may be generous on that. It more than likely was 15 to 17, somewhere in there. But we were seeing an average of about 23%. And then we saw our phosphorus decrease from about 102 to 14.3 on average. So when we put everything together, we put the percent solids, we put the decreased amount of maintenance, the throughput, and if we have 4 operating presses, we're able to eliminate almost one entire shift and focus that towards maintenance of this old equipment. We decided that we needed to just go ahead and put out an RFP for the contract, and based on the selection committee recommendations, we hired US Peroxide, who's our co-presenter today, as our service provider. We've anticipated that we'll have about $150,000 a year in annual savings from just using ferric and decreasing the polymer dose, decreasing maintenance, being able to increase our throughput, and increasing our solids. And so we feel like that's going to be very significant for us in the future. And then that leads us to AF's project. As part of what we were looking at with the ferric, we have also used peroxide within our collection system for years to regenerate the iron. So that's where AF steps in and starts to look at the utilization of it to regenerate that ferric in the collection system to help with our solids throughput.
Thanks. So as Jamie said, they ran the ferric trial. They put out a RFP for Struvite phosphorus removal, leaning towards ferric, and the primary goal, obviously, to remove orthophosphate. Some of the secondary goals were the increased cake solids, polymer usage. We didn't focus too much on that because we know the science between orthophosphate. It inhibits the solids, and by removing that orthophosphate, we're able to kind of increase the cake solids and decrease polymer usage. So we did, and if I have some time at the end, I do have a couple of slides describing why that orthophosphate is actually inhibiting the flocculation of your polymer. One of the added benefits that we saw from the chemistries that we were looking at, again, the primary chemistry was ferric, but we were also looking at a peroxide regenerated iron technology. Both those chemistries have an affinity to reduce H2S and mercaptan odors. So that was an additional benefit that was not stated in the so we looked at the traditional approach, ferric chloride. It's been used pretty widely for phosphate control. It's got an affinity for phosphate. It works. It's been proven time and time again. So we looked at the science between that, and then we looked at our Prytech approach, which is a peroxide regenerated iron approach, and it's basically utilizing iron that's either fed upstream or is background, and use peroxide to kind of free up those iron ions and create a ferric iron through that. The chemistries at the end of the day are both about the same. The end goal is creating ferric and allowing the ferric to bind with phosphate and create your ferric phosphate complexes. So just a little background on why we wanted to look into Prytech. As Jamie said, they have a lot of odor concerns throughout the collection system in Wichita. They currently feed anywhere from 600 gallons a day in winter months to 1,000 gallons a day of ferrous chloride throughout the collection system for odor control, which all that ends up going through the plant and ending up in your solids. So you have roughly 125 to 200 given the season of iron going into your digesters, and that comes as spent iron, ferrous sulfide, and again, as I said, peroxide has the ability to break that bond and create new ferric or ferrous. So again, our options here were either to add ferric or hydrogen peroxide post digesters to precipitate out your phosphates, kind of eliminate your struvite problems. Eliminating your struvite problems gets rid of your recycle loop going back to the head of the plant. So you're getting improved dewatability, but you're also getting added benefits in improved settleability in your primary clarifiers, as well as nutrient uptake in your dairy. So just a little background on the ferric interactions when you're binding with phosphate. Again, ferric has an affinity for orthophosphate, but it has a preference to sulfides. If there's sulfides in your stream, your ferric will be consumed 10 parts to 1 part before it is able to start binding with phosphate. So we saw that when we're feeding ferric, the demand was quite high because you had to reduce your sulfides first, or bind with your sulfides first, and then it would go after phosphates. This is your Prytech schematic. Again, the city of Wichita has some experience using ferrous in their collection system, and they do have certain regeneration points throughout collections to reuse that iron. Our proposal here was to extend that regeneration to the plant, in this case in biosolids, to get a ferric iron in your dew process. So we did a bench scale test to understand the dose rates for both ferric and hydrogen peroxide. The curves kind of land similarly. Don't let that fool you. Ferric on a dollars per pound basis is a lot more expensive than a dollar per pound of hydrogen peroxide. And so we kind of determined what the dose rates would be to get less than the 20 milligrams per liter of orthophosphate, which was stated in the RFP. So we chose 275 milligrams of hydrogen peroxide, 350 of ferric. That's a little small for you guys to see, but we calculated that by using hydrogen peroxide, you're spending around $300 a day versus a ferric chloride feed, which would be $900 a day, almost 33% of the cost. Like I said, another added benefit to the program was odor control. So the red and blue, I'm sorry you can't see the blue, but the blue is actually behind your red. But both peroxide and ferric did really well removing the H2S. Hydrogen peroxide oxidizes the H2S to elemental sulfur. Iron actually binds with the sulfides and precipitates it out. They both do a really good job removing the sulfides. The other odor constituent we looked at was mercaptan, and that's your lower graph. So the green, ferric doesn't do anything for mercaptan. Hydrogen peroxide in the presence of iron actually is a catalyzed reaction and actually creates hydroxyl radicals, then react with your mercaptan. So with the Prytech technology, we were able to reduce both H2S and mercaptan down to 0. With the iron, it was just the H2S. So we ended up starting a Prytech trial. We dosed peroxide. September of 2018 was our first trial run, or actually it was our bench scale test. And with the winter months, we had less iron, so we were actually precipitating out less phosphate during those months, but also the phosphate levels in the digestate were also fairly low. When we started up the program in February, we noticed that we didn't have enough iron in the system. As you can see, we're only precipitating out 20 milligrams per liter. And so our plan forward, we're actually working on adding a supplemental iron injection to add more iron into the sludge prior to feeding with peroxide, and that's actually in the works. We're installing that iron. So for the winter months, we're supplementing iron injection to remove a bulk loading of the phosphate, and then the remaining with peroxide, and that way it saves a little bit of money versus just dosing iron itself. You can see in June we have plenty of iron to precipitate out the phosphate. So the summer months there's not as much supplementation. So really the conclusion, summer months, which is current to date, we're able to precipitate out greater than 100 milligrams per liter of orthophosphate. And as Jamie said, when they did the ferric trial, their phosphate levels were, I think, 103, and they reduced it down to 14. Right now, we're seeing phosphate levels up to 145. So the loading changes based on the sludge coming in. So at times we'll need to supplement with iron. Current cost today is $313 a day, which is what we proposed. As you saw in the February graph, we have a lot less iron. So if we were to supplement, worst case scenario, about 150 milligrams per liter of iron, and then regenerate the rest with hydrogen peroxide, we're looking at a max cost of the combined technology of $600 a day. Whereas with the ferric technology, you're looking at $900 a day on a good day. So an added benefit to the Prytech, iron is trending upwards. I think in the past year or so, iron's gone up about 30%, and it's going to continue to go up. So long-term savings is significantly higher than what they'll be in the future, or sorry, what they are today. Still to be determined. Like I said, we have a little bit higher phosphate concentration in the sludge, so we're looking to supplement with ferrous or ferric iron in the blend tank. So this is post-digestate. It goes into a blend tank, and so we'll add ferrous or ferric iron there, and then the remaining would be with hydrogen peroxide. And so Jamie did a lot of work with the ferric trial, and they were able to understand that there's significant increases. We see those similar increases with our Prytech program. This session came a little too early for us to compile all that data, but we're seeing that now, and we just need to compile it up together. So the technologies are both very similar. The data is just not there yet for us to present to you today. One of the great things with the Wichita plant is they land apply their sludge, and it's used for farming. And we want to see the impact of this added phosphate going to the sludge and what it really has on the effect of growth and the crop cycle. It's not typical that you can just, I think you have a Class A/B sludge, right? Or
It's Class B.
you have Class B. So it's a nice added benefit that we can actually study what this added phosphate in the sludge would do to the growth of crops, and that's something we're looking at in the future. Just some acknowledgments from the city of Wichita. Becky is the plant superintendent, and Tabitha Kling, and of course Jamie. We've been working countless hours on this project, and then Mike Nelson is the regional program manager of the account. And that's really it. Do I have a few more minutes? So, two? Okay. If you guys want to hear about why phosphate is biosolids dewatability, so there's the divalent cation bridge theory, where when you have phosphates in solution, it's kind of consuming your magnesium and your calcium. It's causing an inhibition for your flock to settle out properly. By removing that phosphate, you're allowing your cations to kind of float around in solution and complement your polymer. And so that's why we're seeing such higher solids and improved dewatterability by removing phosphate. Again, that's just kind of the mechanism of how polyphosphates absorb your cations. And just a graph showing as you're removing your phosphates, your free ions, your free cations are more readily available. That's why you see the higher solids.